Okay, as we get into 9.6, then we run into more tests. We're going to do the ratio test here. We're also going to do a root test. But there's some series that don't work very easily with some of the other tests. For example, this is not an alternating series. It's not a P series. It's um, it has some characteristics of a geometric series in that we have a number to the nth power on bottom, but we also have this factorial that makes it not a geometric series. We're changing what the numerator is each time. So um, this one we haven't done any integrations with factorial. Um, it might be a little challenging to do comparison tests or the limit comparison test here. So often when we have factorials involved, and there are some other things where this test comes in well, we do the ratio test. And remember what the ratio test tells us to do. We're taking a limit, and we're taking the nth term, putting it on bottom, the n plus 1 term, putting it on top. So let's think about what this is. If we look at the first term plus the second term plus the third term, fourth, fifth, and so forth. If we randomly pick a term, let's say this one, then if we call that the sub n term, the next one would be the n plus 1 term. So if we take the absolute value of that, that just makes sure that it's positive, then this can converge if we're getting smaller and smaller and smaller, and eventually getting closer and closer to 0. Well, how is that going to happen? If these are getting smaller and smaller and smaller, then this one is going to be smaller than that one. Well, if we divide things, if the top is smaller than the bottom, then that ratio is less than 1. Now, if it's alternating signs, or if we have some positives, some negatives, then it's going to be even more likely to converge because we're canceling things out. We're not just constantly getting bigger. But regardless, whether opposite signs or the same signs, if the following term is smaller than the previous term, and we continue that pattern as n goes to infinity, so the amount we're adding is getting smaller and smaller and smaller and smaller, then we're going to converge. On the other hand, let me flip it upside down. If the following term is bigger, what would that look like? If the following term is bigger, if the numerator of a fraction is larger, then it's bigger than 1. So as we're getting closer and closer to infinity, if the following term is normally larger than the previous term, that one's going to diverge. If that limit equals 1, then it's inconclusive. We don't know what's going to happen. We're not sure, is it going to converge? Is it going to diverge? We don't really know for sure. So our a sub n is n minus 1 factorial over 5 to the n. A sub n plus 1 just means everywhere we have an n, put an n plus 1. Everywhere we have an n, put an n plus 1. And then we're going to divide these. We're going to put this one on top, and we're going to put that one on bottom. So the first one, I'll write it out. We're going to have n factorial over 5 to the n plus 1 divided by n minus 1 factorial over 5 to the n, and we're going to take the limit of that as n goes to infinity. In the future, since we're going to be dividing fractions, instead of writing it as one fraction over another fraction, we'll just write it as one fraction times the reciprocal of the one that goes on bottom, which we're going to have to do that here anyway. So I'm just going to skip this step most times. So we have n factorial. In order to make these reduced, let's call 5 to the n plus 1, 5 to the n times 5 to the first. When we're multiplying and our bases are the same, we add our exponents, so those are the same. When we flip this, we're going to have 5 to the n on top, and we're going to have n minus 1 factorial on bottom. So 5 to the n, 5 to the n, those cancel. In order to reduce the factorial, let's pick the largest one, which is this one, and change it to n times n minus 1 factorial. That includes all the same things. N, the next smallest one, and then this includes from there down to 1. So those and those will cancel. So we're going to take the limit as n goes to infinity. We're going to have n on top, 5 on bottom. As n goes to infinity, that goes to infinity. That's bigger than 1. So by the ratio test, this diverges. This one diverges. All right, let's take a look at another one. This one is another good one to use a ratio test with because it's not alternating series, it's not geometric, it's not p-series, it's not telescoping, and some of the comparison tests would be challenging to use here, perhaps. So our a sub n is 2n factorial over n to the 6th. A sub n plus 1 would be 2. We have to replace n with n plus 1, so we can't just plus 1 here. The n has to be plus 1 by itself, so actually we're going to end up with a 2n plus 2. On bottom is n plus 1, and then that's to the 6th. So I'm going to take the limit as n goes to infinity. This one goes on top, so I'm going to call that 2n plus 2 factorial. On bottom, we're going to have n plus 1 to the 6th. Here, since we're dividing by this one, we're going to multiply by the reciprocal. And we need to put a parenthesis around that because it's 2n, this factorial. It's not just n factorial and then times 2. If we look at our factorials, this is the large one. So let's write out terms until we get, or factors, until we get down to 2n. And then we can keep 2n down to 1 as factorial. So we have this factor. The next smallest integer would be that one. The next smallest integer would be that one. And from here on down to 1, these have all the same factors. So we can cancel that with that. So then the question is, well, what do we do with those? We could, if we wanted to, we could multiply that out. We could use the binomial theorem to multiply that out, or we could multiply it out the long way. But if we think about it, when we FOIL that out all those times, we're going to have an n to the 6th, and then we're going to have something times n to the 5th all the way down to a constant. And in this case, that constant is going to be 1. If we let n go to infinity and we have that the degree on top, the degree on bottom are the same, the leading term here and the leading term here determine what happens. So since those are the same, then our coefficients are going to tell us what that goes to. So the limit as n goes to infinity of this over that just makes 1. So this is the part that we really have to be concerned about. Now, if those were different degrees, then if the degree on top is bigger, it would go to infinity. If the degree on bottom was bigger, it would go to 0. But notice here, if n is going to infinity, then this product is going to go to infinity. And when we do the limit of that, we said that limit goes to 1. Well, infinity times 1 is just infinity, so this one diverges. That one's going to diverge. All right, the next one deals with the root test. So the root test is useful when we have something to the n power. If we have factorials and other things mixed in, that could make it challenging. But what the root test tells us that if we take the nth root of our nth term and we let n go to infinity. So if it's the second term, if we take the square root. If it's the fifth term, we take the fifth root. If it's the 20th term, we take the 20th root. If that limit is less than 1, it converges. If that limit is larger than 1, it diverges. And if the limit equals 1, then we don't know what it does. So similar to the ratio test, if when we take that limit we get just 1, well, we're really not sure what happens there. So here is 1 over 7 to the n. So if we take the nth root of 1 over 7 to the n, and then take the limit, let's see what's going to happen. Ways. Underneath the radical, we could rewrite that as 1 over 7 to the nth power. 1 to any power is 1. 7 to the n power is 7 to the n power. This root and that power are going to undo each other. If you think about rewriting that instead of as a radical, this n is the power, that n is the root, n over n makes 1. But essentially raising something to a power and taking that same root cancels each other out. So we're going to take the limit as n goes to infinity. So the limit as n goes to infinity of 1/7. Well, the limit of a constant is that constant. That's less than 1. So we converge by the nth root test. Or I say the nth root test. Just called the root test. Okay. If we look at this one, it tells us to do the root test. On the test, it might not tell us which test to use. Some of them it might, and then some of them it might just say, use a test, find out the convergence or the divergence of the series. Our a sub n is negative 7n over 6n plus 1 to the 3n. So we want to take the nth root of that, negative 7n over 6n plus 1. They also tell us here, take the absolute value of that. And what that's going to do is just make sure it's not negative, because for some roots, we can't take the root of a negative. So by taking the absolute value, we could drop the absolute values, and the absolute value of that is going to make it positive. So how do we take the nth root of this? Our base is 7n over 6n plus 1. Our power is 3n, and we're taking the nth root. So those cancel. So we need to take the limit as n goes to infinity, 7n over 6n plus 1 raised to the third power. So properties of limits, if we have something raised to a power, we can take the limit of the inside and then cube it. If we take the limit as n goes to infinity, since those degrees match, it's going to turn out that we get 7 over 6, and then we're going to cube that. So 7/6 raised to the third power is about 1.6. That's larger than 1, so since that value is larger than 1, our series is going to diverge. If that was less than 1, it would converge. Okay, this one tells us to determine the convergence of this series, but it doesn't tell us which method to use. So we have to make that determination on our own. If we take a look at this one, we have a -1 to a power, so that's going to make us alternate signs back and forth, back and forth. We don't have any factorials, anything like that. We don't have anything to the n power. So let's just try to use the alternating series test here. For the alternating series test, remember how that works. We need to take the part that it says to take the absolute value of it, which basically means drop the part that's alternating, and we need to see what that's going to. Is that getting smaller and smaller and smaller? So n, our a sub n plus 1 would be 3/n plus 1. So is a sub n plus 1, is that smaller than a sub n? Now we said sometimes it might not be to begin with, but after a while it has to start getting smaller. So if we clear fractions, we would have 3n is less than or equal to 3 times n plus 1, or that would be 3n plus 3. Subtract 3n from both sides. Is 0 less than or equal to 3? Well, yes. So a sub n plus 1 is less than or equal to a sub n. A sub n does go to 0. So by the alternating series test, this does indeed converge. If we take a look at this one, notice the top is a constant and the bottom is a constant, or has a multiple, a factor that's a constant. We can pull those constants out in front of our series. Every single term in our series is going to have 10/3, 10/3. So we can pull that common factor out and call this 1 over the square root of n cubed. And whatever happens to that, if that converges, then what it would actually converge to is 10/3 times that convergence. If this goes to infinity, multiplying it by 10/3 is not going to keep it from going to infinity. So if we can determine what happens here, then we should be good to go. So let's rewrite that as 1 over n to the 3/2 power. So this is a p-series. Remember, n is 1 to infinity. Our p is 3/2. That's greater than 1. And remember, with a p-series, p greater than 1 is going to converge. It will converge. And then the last one we're going to do here. Several different ways we might could look at this. One thing, look at the fact that this is alternating. But we have some n powers. We don't have any factorials, but we do have some n powers. And then we have another factor that's an n. So it might be challenging to try to show that if this is a sub n, it might be challenging to show whether or not the next term is going to be smaller or larger. I mean, if we think about it, as n gets bigger, then this is going to get, the top is going to be 3 times as much, the bottom is 2 times as much, but then this n is going to be affecting it also. So it's going to make the bottom get bigger and bigger and bigger as n gets bigger, which is going to make the whole thing smaller. So which one wins out? Does the 3 getting bigger on top faster than the 2 win out? Or does the n on bottom that's getting bigger win out? We could do it that way, but let's maybe try another test. So the ratio test involves dividing those, taking a sub n and a sub n plus 1 and dividing them, and we also take the absolute value. So since we're taking the absolute value, the part that makes it alternate, so the n plus 1 would make that 3 to the n plus 1 over n plus 1 times 2 to the n plus 1. N goes to infinity of the absolute value of this one, which is 1 negative, divided by that one, so times the reciprocal. So this is a to the n plus 1 over a sub n, absolute value of that. So hence our negatives went away. So we need to simplify this a little bit. We can rewrite this as 3 to the n times 3 to the first. We can call this 2 to the n times 2 to the first. So that 3 up to the n and that 3 to the n cancel. That 2 to the n and that 2 to the n cancel. So what are we left with? We're left with a 3 on top. We're left with a 2 on bottom. We're left with an n on top. And we're left with an n plus 1 on bottom. That 3 halves we could pull out front because that's just a, those are just factors. And then we take the limit, n goes to infinity of that. That's indeterminate. I take the derivative of the top, we get 1. The derivative of the bottom, we get 1. So the limit of 1 over 1 is just 1. So we get 3 halves. That's more than 1. So this one diverges. That one's going to diverge. Now let me just finish up with a comment. You could have the same problem as someone else on the test, but you might show its convergence or divergence using a different test. There's more than one test that can be used on some of these. Some of them, there's a specific test that's the easiest way to do. But what's important is that you find out the proper part, whether it converges or whether it diverges, and also that you prove that that's the case. If you just guess and say, well, I think it's going to diverge, well, you might guess correctly, but you have to show why that's the case. You have to tell me which test you're using. So in this one, we use the ratio test. So you have to tell me which test did you use. And then you have to show me using that test that it really does diverge.